Hello, my name is Professor Rad, and in this video we'll be talking about how do you compose linear transformations. So let's get started with a definition about what it means to compose functions, and then we have a theorem, and we'll work through an example as a follow-up to where we left off in the last video. So for definition 3, we're defining what it means to compose linear transformations. So if you want to pause the video and copy down this definition, now you may. But basically, it's the very same sort of definition as if we have just functions that you're used to. So if t is a linear transformation from u to v, and s is a linear transformation from v to w, then, and we need u, v, and w to be vector spaces, then the composite of s and t is going to be s composed with t. It goes from u to w, so where t started and where s ended. Right, so that's why t has to go to v and s has to start in v. So, right, you take the train of the t train to city v, and then you pick up the s train and you go to city w. Then s composed with t of a vector v is the same as s of t of the vector v. And we have a nice theorem here that says if my first linear transformation t is induced by matrix A and s is induced by a matrix B, then their composition is induced by the matrix BA. So in this case, S is induced by the matrix B, so it goes on the left. And this kind of matches a little bit what we were seeing in our example on the last video, where we first multiplied, I believe we multiplied a vector xy by this matrix, and then we took that result and we multiplied it here. So if I had my vector v, lowercase v here, then I multiply it by A first, and then multiply that result by B. So what we're going to do to start is to see if we actually get the same vector. So in our last example in the last video, we did S first and then T. So really, this matrix is the matrix that's inducing T composed with S, because we did S first, so S would be the first transformation, and then we did T. So according to theorem 4, we should get this matrix by multiplying the matrix for the linear transformation A by the matrix for the linear transformation for S. So let's see if that's what we get. So I'm just going to work that out in the space on the bottom here. But I think if you're following along in your notes packet, that would be example 9. Okay, so in example 9, we're just confirming this theorem. So since, again, we did t composed with s, we've got to have the matrix for t first. So we're going to have 1/2 root 3 over 2, and then negative root 3 over 2, and 1/2. This was a rotation through the angle pi thirds. And then we have the matrix for s. This was a reflection over the line y equals negative 2x. And we want to see if we get this matrix in the end. So let's carry out our multiplication here. So 1/2 times negative 3/5 is going to give me a negative 3/10. And then this is going to give me a positive 4 root 3 over 10. Then in the top right, I have, that's going to give me a negative 4/10. And I'm leaving these unsimplified for reasons. Then we'll have a negative 3 root 3 over 10. And then for the bottom left, we'll have negative 3 root 3/10 minus 4/10. And then we'll have negative 4 root 3 over 10 plus 3/10. So I wanted to keep these all with the same denominator so that it makes it easier for me to combine my like terms. So let's combine them so that the radicals are second when I write my answer. It doesn't really matter, but I just want to be consistent. So negative 3 plus 4 root 3 all over 10. And then here we're going to get a negative 4 minus 3 root 3 all over 10. And then negative 4 minus 3 root 3 all over 10. And 3 minus 4 root 3 all over 10. All right, so let's see if this matrix that we got just by multiplying these two was the same as what we got at the end of the last video. And it appears to be so. Fabulous. There we go. So this isn't a proof of theorem 4, it's just kind of like an application of the theorem. So now for moving forward, if we want to find the composition of two linear transformations, and we know the matrices that induce those linear transformations, we can just multiply those matrices in the correct order, because remember, matrix multiplication is not commutative, so you do have to pay attention to that. But as long as our order is correct, we can find the matrix. So let's go ahead and do another example. All right, in this example, we're going to venture away from Rn and Rm for a moment and go back to some wacky vector spaces. So we are going to start out in R2, and we're going to map to P2. And then we're going to pick up in P2 and then go to N22. So we're kind of involving lots of different things today. So the transformation that gets us from R2 to P2 is called T, and T maps the vector AB to the polynomial ax squared minus a plus b x plus b, and S maps a polynomial from P2 to a 2 by 2 matrix by going ax squared plus bx plus c, taking that to AB, negative b, and c. And we want to find an equation for the composition. Now, our first question is, does theorem 4 apply? In this case, it doesn't, because we don't have these transformations defined by matrices. So if we could find a way to define these transformations by matrices, fabulous. We could then multiply them, get the composition, really nice, but we don't. So we're just going to go through this the old-fashioned way, and we're going to take a vector, throw it into T, take that result, and then throw it into S. So let's start out by finding T of our vector V. So this is T of, just use AB, and we know it gets sent to this polynomial. All right, cool. Now, what you want to be careful with here, both of these are using A's and B's. Notice I'm using A, B instead of X, Y, and you want to be careful when you're mapping from like Rn to Pm. So because polynomials use X as part of the definition of the objects, you want to stick to other kinds of values for your vector in R, whatever. So that's why I'm using the A and the B. And now when I go and throw this into this function, or this transformation S, I have to be careful because these A's and B's are not the same as these A's and B's. Okay? So I'm going to take S of this result, so ax squared minus a plus b x plus b. Now what this function or transformation does is it makes the top left coordinate the same as whatever the x squared coefficient was. So our top left coordinate is going to be a. That was the coefficient of x squared. That stays the same. The top right coordinate is the same as the coefficient of x. So over here, our coefficient for x is negative a plus b. So the top right here is going to be negative a plus b. The bottom left is the negation of that, so we can just take off that minus sign and we'll get a plus b. And then the bottom right came from the constant term. So our constant term here is b. So to wrap this all up and write an equation for S composed with T, we would have S composed with T of the vector AB is going to equal the matrix A plus B, negative A plus B, B. Ta-da-da-da-da-da-da. All right, there we go. So we just found another composition of functions. So that's going to wrap it up for this video, but think back to when you first learned about functions and you composed them, and then you found out like, oh, there are these really cool functions that like undo each other when you compose them, right? We're going to call those inverses because they like inverse each other, right? We take you back to the beginning. So guess where we're heading next in our next video? We're going to find inverses of linear transformations. We'll see if they exist. So I'm looking forward to seeing you then. In the meantime, I hope you have a wonderful day. And yeah, bye for now.